Hi, everyone. My name is Danielle Frostig. I'm a graduate student at MIT, and I'm excited to tell you about Winter, a new near-infrared survey telescope we're building here at MIT in collaboration with Caltech. Winter stands for the Wide Field Infrared Transient Explorer. It's a seeing limited all-sky survey on a dedicated 1-meter telescope with a greater than 1 square degree field of view. We observe in the near-infrared Y, J, and shortened H bands down to a depth of 21 magnitudes in J band. A big part of this project is the development of in-gas detectors as a cheaper alternative for traditional near-infrared astronomy detectors. We think this near-infrared telescope will be a great complement and precursor to the Roman Space Telescope, and we share many of the same science goals that we're talking about at this meeting, including multi-messenger astronomy, and we've designed the instrument around kilonova discovery from gravitational wave follow-up, and you should listen to Viraj's talk during the multi-messenger session, where he tells you about the very exciting prospects we have for kilonova discovery. And we're also interested in the same dusty environment, static sky science, and exoplanet science in the near infrared. Here's our 1-meter telescope in its dome at Palomar Observatory. We have an optical camera on one end and the Winter instrument on the other end. It takes the light from the 1-meter telescope and splits it up into 6 different channels with this fold mirror after passing it through a different filter to select our color. And we can split the light up into 6 different detectors, 3 on each end, to get a relatively large field of view with this bonded tiled optical design so that we get a relatively large field of view for this instrument. We've been observing robotically with the telescope since summer of 2021 with an optical camera, and the near infrared Winter should be on sky this year. There's many papers you can check out to learn more, and feel free to email me at this email address if you have any questions. Thank you for listening.
I'm Mitchell Carman, and I'll be presenting work that I've done with Samantha Dixon, Saul Perlmutter, and the nearby supernova factory at Lawrence Berkeley National Lab. We developed a neural network, which we call embed to spec, which can be used to generate spectral time series of type 1a supernovae from 10 days before maximum brightness to up to 40 days after. It can be used as a generative model of type 1a spectra and can be used for precise standardization of 1a brightnesses. So first I'll go a little bit into how this neural network works. Our work is based on the twins embedding developed in Boone et al. 2021, which is a 3D nonlinear parameterization of the diversity of 1A spectra. The twins embedding is used in the Boone work to standardize 1A brightnesses given spectra at maximum. However, we wanted to see if the same information is present in the entire spectral time series. So to accomplish this, we built the embed to spec neural network and generative model. The neural network is simple. It takes a supernova's embedding coordinate in a given phase up to 40 days and produces the SED that we'd expect to see. The full generative model also includes a dust extinction parameter and a magnitude offset that we manually model in as well. So the model's performance is showcased in the top right in figure 3. The generative model has many uses we want to explore. Namely, it can be used for precise brightness standardization given an estimate of a 1A's maximum brightness. So by fitting twins embedding coordinates to observe spectra, we can improve SALT2 magnitude estimates and reproduce the work done in Boone et al. That uses spectrum at maximum. This enables high-precision distance moduli using spectra at later phases, and is even shown to suppress host galaxy step systematics. It can also be used to simulate observations of spectra, such as those from the Roman prism, and can be used to simulate light curves. Combining this generative model with kernel density estimation of the model parameters, we can simulate sets of 1As that capture the full diversity of 1A spectral features. We're really excited to present this new tool for supernova cosmology and are about to submit a paper detailing our work for publication. My email is in the bottom right corner of the poster if you'd like to discuss any of this further. Thank you so much.
Hello, my name is Erin Hayes, and I work with Helen Chu and Misao Sako in the Department of Physics and Astronomy at the University of Pennsylvania. Today I'm going to be presenting SCONE, which is a convolutional neural network that is able to classify 14 different types of transients and variable objects in the plastic data set. So to begin, SCONE's pipeline is split into 2 parts. There's first the pipeline for the variable objects, which are objects that exhibit repeated changes in brightness over time, such as mirror variables, M-Dwarf flares, AGN, etc. And then there's the transient pipeline, which exhibits a single change in brightness over time, such as type 1A or other supernovae, or microlensing events, etc. These objects are then fit with Gaussian process regression and turned into 2D images. You can find more information about that process on my poster. which are then a convenient format to feed into the convolutional neural network. And to present some preliminary results, we've had great success, although the process of creating scone is not yet complete. But as you can see here, the scone does a very good job, particularly with transients. It reaches almost 85, almost 90% accuracy. With variable stars, the results are not as clear cut right now. There's clearly an issue, as you can see here, with because of the issues with the validation loss. There's clearly an issue with the fitting, possibly overfitting, that we're still working to resolve, but the potential is there with it already achieving about 70% accuracy. And with that, I invite you to check out my poster to learn more. Thank you.
Hi, my name is Zoey Fox, and I am a JWST instrument scientist at the Space Telescope Science Institute. And I'm here today to tell you a little bit about our poster and recent paper on a Spitzer infrared survey for dust-obscured nuclear supernovae, and the implications that this might have for Roman down the line. Right off the bat, the takeaway is we discovered 5 supernovae that were not discovered at optical wavelengths, and we describe why that's important in the broader context of supernova rates throughout this poster. We start off with a discussion of the missing supernova problem, namely that the observed supernova rate, particularly at high redshifts, is not consistent with the number of supernovae predicted by the star formation rates alone. We describe a great way around this, or actually through this, is with infrared observations due to lower extinction. And we go on to describe our survey and image subtraction technique, which uses forward modeling, which is something similar that Roman will be using. We then describe our results, 9 supernovae discovered, 5 of which were not discovered at optical wavelengths, and we describe our beautiful press release image here, which does use real data. And finally, we talk about these results in the broader context of the predicted supernova rates, and we show that an infrared survey can help resolve the missing supernova problem. That said, this was a limited survey due to Spitzer's field of view, its sensitivity, even its wavelength regime. And there's a lot more work to be done, which will really be optimized with Roman. So I'm looking forward to those observations, and if you have any questions, come by, check out my poster, and feel free to ask. Thank you.
Hello everyone, I am Ankurkos and I am going to talk about the search for the merger ejecta emission in short GRBs. This is the snapshot of my poster. So the short GRBs are thought to be coming from the neutron star mergers. During the merger, tidal disruption of the neutron star occurs and the ejecta produces if the resultant product of the merger is a magnetar. Due to its continuous injection of the energy via spin down process, boosts the velocity of the ejecta. When the energetic ejecta interacts with the circumstellar medium, it produces the long-term emission which peaks in the low frequency radio regime. This is the expected spectrum which peaks around 600 megahertz. This is the motivation behind the selection of the GMRT for our observation. The GMRT data has been reduced by APES and CASA. The contour maps and the upper limits have been given in figure 2 and figure 3. So prior to our study, 4 attempts have been done. So in this study, we have done 2 corrections. One is the wide observation span, another is the proper frequency channel. We have also corrected the relativistic correction by considering the evolution of the bulk chlorage factor in the model. So here you can see with the help of these 2 flux and the time equation, we can construct the model light curves. Here we have plotted the model light curves along with the 3 sigma upper limits for the 2 GRBs with the varying number density. So the left hand side represents the light curve of GRB 140903, which is the highest energetic case, and the right hand side depicts the picture of GRB 160821b. This is the lowest energetic case. So GRB 140903a is the only GRB for which the highest energetic model is valid, and the number density can be constant in between 10 to the power minus 2 to 10 to the power minus 1 centimeter to the power minus 3. On the contrary, the GRB 160821b, the lowest energetic model is valid only for the lowest number density model. So with the help of the model light curves and the 3 sigma upper limits, we can constrain the energy injection from the central engine, the number density of the ambient medium, and the microphysical parameters associated with the burst. So thank you.
Hi, everyone. My name is Goku Srinivasaraghavan, and I am a first-year PhD student at the University of Maryland College Park. My poster summarizes a paper I first authored, currently in the revision process, on supernova 2020 QMP. I wanted to do something a little different in my pop video. I think it's important to remember that behind every scientific discovery is a story behind the people who made that discovery possible. Here's mine. This is supernova 2020 QMP. Around 50 million years ago, a star reached the end of its life, shedding its outer layers and underwent a cataclysmic explosion. In the summer of 2020, the Palomar-Gattini Infrared Survey detected the explosion. A junior undergrad was given the opportunity to lead a paper on the event. That student was me. At the time, my life was in disarray. One of my biggest passions had been taken away from me. My once promising basketball career, one that I planned to continue with professionally, was stripped away from me due to debilitating knee injuries. Space had always been my other passion, and I knew I was in a blessed position to make the transition to the next chapter of my life. But doing so was incredibly hard. My heart would always long to be back on the court, so much that I lost my sense of identity and confidence. Every day became a struggle. However, Supernova 2020 QMP changed this. Through my work on a supernova, I found a new sense of identity as a scientist, and I finally was able to make the transition into the scientific world happily. During the time I worked on the paper, I finished a senior thesis, graduated from Caltech, and began graduate school. This project is a culmination of my undergraduate years defined by perseverance, soul-searching, and an unwavering resolve to be resilient in my passions. In my poster, we summarize the main results of the paper, including deriving the progenitor mass and explosion energy of the supernova, interesting radio observations, and a core collapse supernova simulation, illustrating the advantages of near-infrared surveys to detecting extinct supernovae. Thank you everyone for listening. I hope you have a great rest of the conference.